Okay, so we're going to continue with 14.1. We left off with this exercise where we wanted to find the domain, the range, and the graph. So for this particular exercise, again, it may be useful to uh, to sort of change the form by rewriting it with a z instead of f of x, y, and then doing a little bit of manipulation. So notice here that we have z minus 1 is equal to this square root of x minus 4 squared plus y squared. And when you square both sides, you get z minus 1 squared is equal to x minus 4 squared plus y squared. And this is kind of just a shift of what probably may look more familiar, which is z squared equals x squared plus y squared, which is our cone. And all it is, it's shifted sort of the base of the cone. And remember that because we only have the positive square root here, only positive square root means we only have the upper part, the upper half of the cone. Again, the total cone is not a function. It fails the vertical line test. So what we do is we say, okay, here is our coordinate, our three-dimensional coordinate system. We just bump over 4 units in the x direction. Here's 4. And we bump up 1 unit in the z direction. And our base of the cone is sitting right here at the point 4, 0, 1. And then the cone sprouts up from that place. And so once you see the graph, well, even before you see the graph, I suppose, you can clearly see that the domain of this function is all of R2, or all of the xy plane. So you have all x coordinates, all y coordinates, and that forms the domain of this function. And you can see that because, well, inside the square root you have the sum of squares that's always positive, or at least non-negative, so you can plug in whatever you like. For the range, it may be convenient to note that the smallest z value is equal to 1, and then it just grows from there. So hence our range is 1 to positive infinity. Okay, so that was our exercise from last time. There's one little last part I want to talk about, which is about level surfaces. So we've seen level curves before. What are level surfaces? Well, let's consider a function. We'll call it capital F, going from R3 to R, which means we're sending x, y, z to some capital F of x, y, z. So that if you, well, in theory, if you wanted to graph this, this would be something in 4 dimensions, in 4D space, which is slightly hard to graph. Maybe some of you can do it. I certainly have trouble. So what is the graph by definition? It's the set of all x, y, z, f of x, y, z, where the points x, y, z run in whatever the domain is that they're sitting in. Of course, maybe the domain is all of R3, maybe the domain is not. But that would be what the graph is algebraically. And so because it's challenging to graph, we consider what are called level surfaces. And those are best seen by just taking an example. So here's an example. F of x squared equals x squared plus y squared plus z squared. Now, what are the level surfaces? So the question is, what is a level surface? Well, what is a level surface of this, of capital F? Well, it's just the analog of level curve. We set f of x, capital F of x, y, z to be equal to some constant. And this is going to give us a surface rather than a curve. So for example, in this case, let's take c equals 1 and c equals, say, 4. What would we get? If we have f of x, y, z is equal to 1, then we have the equation x squared plus y squared plus z squared is equal to 1. Or in this case, we have f equaling 4. So x squared plus y squared plus z squared is equal to 4. And you can see that these are all spheres centered at the origin. So the level surfaces, you can think of these basically like an onion. They're concentric spheres. So here's a sphere of radius 1. Just dot the back part here. So this is c equals 1. And then if you grow a little more, you'll have another one here sitting, and with slightly larger radius. This would be c equals 4. Of course, at the center, there'll be a dot, which is c equals 0, where x and y and z are all 0. So the level surfaces sort of, when raised, quote unquote, to the 4th dimension, will form the graph. Now you say, okay, well, what is the use for that in R3? Because we're concerned with 3-dimensional coordinates. Well, a lot of surfaces that we consider are level surfaces of a, I'll just call it a 4-dimensional function, capital F. So for example, if I wanted the full cone, which is z squared equals x squared plus y squared, I can't write that as a function, but what I can do is say, okay, here's capital F of x, y, z, which is x squared plus y squared minus z squared. Well, if I set f of x, y, z equal to 0, so that c is 0, this corresponds exactly. This is x squared plus y squared minus z squared equaling 0, which is the same as z squared is equal to x squared plus y squared. And so this is the cone. In fact, the level surfaces of these are cones. So we can derive surfaces that are not functions. So a lot of this time, even if they are functions, you can do this, but all surfaces are level surfaces of some 4-dimensional function. So hence the level surfaces concept comes into play, and we'll see more about this later on. But this is a very useful concept. This is a very useful concept. We'll see this especially, I'm just going to give a little hint about this, when we see what's called the equation of the tangent plane. So this is basically the idea that if, and we'll formalize all this later, suppose you have a surface that's something like this, and you take a point right here, it turns out there are tangential directions in all directions, really. These are tangential directions, and we'll, again, formalize all this later. But if you take the collection of all tangential directions, it forms a plane. And this plane is called a tangent plane. And if you want to compute the equation of the tangent plane, the most general formula for it involves the use of the level surface. So we'll see this a little bit later on, but I wanted to introduce the idea of the level surface. We'll conclude right here. So this is the end of 14.1, and we'll start 14.2 in the next video.